record this computer. So data encryption standards is the second part of the lecture, and data encryption standard is issued in 1977 by NIST, or the National Institute of Standards, and was the most widely used until 2001 when it came the advanced encryption standard. So we have two different algorithms here, data encryption standards that we are going to talk about today, and we have advanced encryption standard, which we will introduce in next lectures, inshallah. So this is mainly, this continued for a long time because at that time they don't have a strong parallel processors, they don't have a strong parallel processing power as we have right now today. So it was very difficult to decrypt or to break that cipher at that time. But at 2001, around or 2001, somebody has broken the this standard, or the cipher of this standard, using the parallel processing or the processing power that increased day by day. After that time, they have developed another one, which is advanced encryption standard. At the beginning, that algorithm was named data encryption algorithm, or DEA. That was its name. Actually, this, or data encryption standard, encrypting data in 64-bit blocks. So this is the size of each block using 56-bit key. So we have 56-bit key is very weak. Nowadays, this is very weak key. I will tell you why it is weak in another slide. The algorithm transforms the 64-bit input in a series of steps into a 46-bit output. So it takes input as 46-bit and output 46-bit too. The plain text is 64, and the output, or the ciphertext, is also 64 bits. The same steps with the same key are used to reverse the encryption. This means we have the same steps as we told you about the Feastal cipher. We have the same steps in encryption, the same steps in the decryption, the same steps exactly. Maybe they are different in the order, but actually they are the same steps. For example, the swapping of the two right and left is done, and even is done in the decryption. Okay, they are the same, exactly the same steps. But actually in the encryption, we start by K1 to K16, and in the decryption, we start by K16 and end with K1. So maybe this is the difference. Maybe this is only the difference. Okay, so they are the same steps. So we don't need different algorithm, one for encryption and one for decryption. That's the main characteristic of this type of encryption. Also, for data encryption standard, we have the same scheme. So let's look at the data encryption standard here. We have the initial permutation. Sorry. We have the initial permutation. We have the 64-bit plain text. We have initial permutation here is just permutation of the text, just to change the order of the text. And then we apply the same rounds as Feastal cipher, round 1, round 2, until we have round 16. And then we have that swapping, and that swapping is done as done in the exactly in the Feastal cipher. So we have here 64-bit. The 64-bit is divided to two parts. Each part is 32 bits, and we swap these two parts. And also we apply the inverse initial permutation. We apply here the initial permutation, and here we apply the inverse initial permutation. Why we apply the inverse initial permutation? To be able to apply the same algorithm in the decryption. That's why we use initial permutation, and we remove the effect of the initial permutation back in the last round, just to make sure that we are using the same algorithm in encryption and decryption. For the key, we have a key here to the right, is a 64-bit key, and we extract from that 64-bit key, we extract for each round, we extract a 48-bit key for each round. The extraction is done by left circular shift, followed by permuted choices. And these permuted choices is done by S-box. I will tell you also about S-box in a subsequent lectures, not slides, lectures. So we'll talk about the permuted choices here. But anyway, I just want you to know that we have a key, and this key, we use it to create multiple keys. That's what I want you to know now. We have one key, and we created multiple keys, K1, K2, K16. And this key is created, the keys which are created, or the sub keys, should be different, completely different from the original key. That's why we use permutation, changing the order, changing the values, changing everything, just to make sure that this K1 is completely changed when it is compared to the original key. That's why we have these rounds here. So this is mainly the data encryption standard and the scheme of data encryption standard. If we want to take about an example, we have here a plain text. This plain text is a block, and this block is passed to this with a key, and this is the key, and the output is the ciphertext here, and we can go step by step to see the output of each stage. Actually, you look at the right hand side and see we have here Li and Ri is the 46-bit block divided to 32 bits here and 32 bits here. This is hexadecimal, means we have 1, 2, 3, 4, 5, 6, 7, 8, 8 multiplied by 4. 8 multiplied by 4. Why? This is hexadecimal. Hexadecimal, this is 5 in hexadecimal, and this is A in hexadecimal. And you know that hexadecimal is represented by 4 bits. So we have mainly here 4 multiplied by what? By 8. 4 multiplied by 8, which is 32. 32 plus 32, we have 64. This is the block size. This is the left hand side part, and this is the right hand side part. Actually, as we have seen in the Feastal cipher, we swap, just swap the right hand side to the left hand side. Each cycle do the same. We do the same for each cycle. We just swap. Okay, it's clear now. We are swapping from the right hand side to the left hand side in the next round. And this one is not exactly the same, but we have function applied to the data. So will not be the same because this is not actually direct swap, but it is a swap after applying a function. So this is the output of that such function. Don't worry about the implementation of function because at that time, you know, the implementation of such function, you will find it is really little difficult. Okay, so don't worry right now. We will talk in detail about such functions. Okay, so now we have the left hand side is swapped to right hand side, but with the specific with the specific function applied together with that key, which is K1. This is this is K1. K1 is passed to that function together with the left hand side. The output is that value in hexadecimal. For each round, the same thing. So this one is here, that one is here, and so on. Okay, this is the initial permutation. Actually, this is not, if you see, this is initial permutation. We return back here. You look at the plain text 0, 2, and 2, 0. It is palindrome. You know about palindrome? It's not palindrome, it's symmetric. We can say it is symmetric. You can read it like that or read it like that. So it's symmetric, and we can make sure that it's palindrome if we can read it from left to right and right to left, the same thing. This is palindrome. Yeah, exactly. It's palindrome. He said that it's palindrome. So this text, if you look at it, is changed. The order is changed here. This is the initial permutation. And even maybe some values. Okay, let's return back. We have 8 here. Okay, so permutation is not a simple permutation because 8 is not here. If you see, 8 here is not here. This means that is not just changing the order, maybe changing the order. We have to get inside this function to see it. And in all our subsequent chapters, I will tell you we are dealing with black box or blocks. Because if you get into these blocks, you will find another blocks, and each block you have to understand the internal structure. We are dealing with them as black box design. So we have internal permutation, and we have the initial permutation and the last permutation, which is doing the same, the opposite input permutation. Okay. Any question here? Any question?
Doctor, can you explain the last row, DA02? How did you get that one? Because it's completely different from round 16.
Yeah, this is because this one, this we have a swap here. Here, this is a swap. So this is a 32-bit swap. Maybe it is direct swap. Okay, let's see if it is direct swap or not. So this is should be the same.
Yes, that's what. It should be the same 25, 8, 9, like that, right?
Yeah, you know it's applying the last permutation, and before it we have a swap. Okay, to make sure of this, you can make sure that all letters here are the same letters here. You can make sure of this. If it is not that, so that swapping is not direct swapping. But actually, if you look at 7, yeah, there is no 7 here. What about 5? There is no 5 here. Yes. So this is not direct. This is the last one. Okay. This is round 16. Let's get back. This is good question. Here, round 16. So we apply the key, K16, and you get the output. And you get the output. And that output, we apply the permutation, the inverse permutation. Okay, so now I understand because you know the initial permutation is not just a change in the order. I told you it is a black box, okay? So it is doing something with letters, and we don't know what it is doing with letters actually. So let us move to the inverse one, which is doing the inverse. It is not really changing the order of the letters. This is the output after the initial permutation inverse. It is after the initial, not the output of round 16. Okay, you get it now? So we have this one. Okay, we have that output, okay, is passed to the this function, whatever it is doing, and then we get that output. Okay, now is okay.
Yes, doctor.
Yeah, this is not swapping actually. All previous rounds are swapping, but now the last one is not normal swapping. It's just applying the inverse permutation, or the inverse of the initial permutation. Okay. There is an effect is called avalanche effect. Avalanche effect is just if you made a small change, just a little change will destroy or change the entire structure of the system. So if you, for example, if you removed a brick from a building, this will destroy the entire building. So little change will lead to big change. Little change will lead to big change. So for example, here we removed, for example, just a little movement in the layers of snow here may lead to that effect, which is very huge effect compared to just a little change in the layers of snow here. So if you make little change, you will lead to big change. This is another name for what? You know, another name for what? We talk about something like that.
Diffusion.
Yeah, exactly, diffusion. This is another name for diffusion. So avalanche effect, we have to take care. We have an input plain text. We have to make sure that any small change in the input text will lead to big change in the output text, or the output or the cipher text. Okay. Here we calculated the avalanche effect in this, or the data encryption standard. And here we have two different strings, but the difference is not big. It is just small change. 0000 is changed to 0001. So one bit it changed from 0 to 1. Just one bit is changed. Here, okay, let's concentrate in this. Okay, here we have the input. There we have the output. Here we have the input, and we have completely another output. And here we have a sigma, which is a difference, a number of bits, the discrepancy, or the the correspondence, the change in the correspondence. We have one bit change, or the change between that one and that one. Just for example, here we have zero, here we have zero. There is no change. We have one here, we have one, no change. But if we have zero here and one here, we count. If we have one here and zero here, we count. This is just one. And here we have more than half of the data is changing. More than half of the data is changed. Okay? You understand the avalanche effect here? Any question? Okay. No news, good news. Okay. What about the avalanche effect in this, but for the key? If we change the key here, we have here the key, that just a little change in the key. We have here the original key, and we have here the key after just changing one bit. Okay, actually this is not zero, it is 0, 0, 4 zeros. This is 4 zeros because this is hexadecimal. And here this is 0, 0, 0, 1. Actually this is not 1, it is 0, 0, 0, 1, because this is hexadecimal, not binary. So we have a change here in the fourth bit. If you read here, you will find fourth. Maybe this is confusing for some students because they say this is the first bit, 0 to 1. No, it is not the first bit. Just because this is not a binary, it is hexadecimal. So here is 0, 0, 0, 0, and here is 0, 0, 0, 1. So actually the change is in the fourth bit. We changed just a little change in the key, and we see that there is no change here in the input data. Input, this is the input data, not the key. We have no change here, but for the second round, we have 3 bits changed. Here we have 11. We have at the round 8, we have more than 32 bits are changed. And that's a huge number. So the avalanche effect is found here. We just change just a little thing in the key, and we get completely different output ciphertext in each round. This is about the performance for each scheme. For here we have this encryption. We'll talk about AES, okay, and triple and triple this. This is another version of this and more stronger than it. And the AES also with different key sizes. This is 128 and this is 192. This is AES but with different key sizes. And this is the last one, AES with 256 key size. This is a very strong one. Let's get back to the first one, which is our algorithm today. The key size is 56. And the number of alternative keys are 2 to the power 56. This is straightforward if you know about binary numbers. We have 2 to the power 56 possible keys. The time required, if we have a speed of 10 to the power 9 decryption per second, this will take 1.1 years. It's about 1 year just to decrypt this key, to decrypt this algorithm, or to break the cipher of this algorithm, or to understand the algorithm behind that, or to break the cipher simply. But now we have improved the performance of computers with parallel processing and the cloud computing and the clustering and parallel computing, parallel processing. I know about all of these because you are from hardware background. We have advanced we have advancements in this field. Now we can get 10 to the power 13 decryption per second. This leads to 1 hour only. For 1 hour only, we can try the brute force attack. We try all the 2 to the power 56 keys and until we get a pure text or clean text. Okay, so now we can break the cipher of this in just 1 hour, just using our modern computers. But before, they need 1.1 years to break this cipher or to try all possible keys. I know maybe you forget about chapter 2, not chapter 1, chapter 2 about Caesar cipher. We tried all possible keys, which was very simple, which is the number of alphabetic or the number of alphabets, which is 26. We tried 26 different trials. This is brute force. Here we don't have only 26, we have 2 to the power 56, which is a very huge number. But we don't try it by hand, we use computers. So we use computer to decrypt or to try all possible keys until we find the key that is used in the encryption. How to know that? Just if you see a plain text, a plain English, you see a plain English, you know that you reached that key. Okay? Any question in this
Doctor,
slide? Yes.
yes, number of alternative keys, 2 to the power 56. How we notice that it's 7.5 times 10 to the power 16?
It's just by multiply. This is by calculator. Just use your calculator. Okay? This is just a calculator. Okay, let me do it by hand right now. Okay, let me see. I can share my screen just to let you see here. Search for calculator. And then, can you see the calculator?
Yes, doctor.
Okay, I take the standard one. This is very simple. If you do like to the power, I think this is not here. I think it is in scientific. Yes, this one. Okay, this one you can use 2 to the power 56 equal. Yeah, this is the number. Okay, you can translate this to the power 16 because we have 9, 3, 6, 9, 12, and 15. So this is 7.5 multiplied by 10 to the power 16. Okay, you understand now?
Yes, doctor. Thank you so much.
Okay. Any other question?
It's enough for today, right?
What?
Is it enough for today?
Okay, give me just few minutes. Another few minutes,
Doctor,
okay?
you what's important for the quiz?
I told you just to study 3 chapters, and I told you you skip the first one. That's what I told you about that. I will not tell you which part you concentrate, which part you don't concentrate. Okay, I just help you by skipping one chapter because it's long and contains many theoretical parts.
Okay, doctor, I have only one question. About the decryption and encryption, we use the ciphertext on the Google to encrypt or decrypt the text. We will be having this also in the quiz?
No, this is a lab, right?
No, it was in lab and it was in lecture too also as well. That's why I'm
Yeah,
asking.
you are talking about the Mac hash calc software. The software
Yes.
is hash calc. No. I will do the same thing just simply, if you need calculation or something, I will put it in the paper. Okay. You,
So like
if you can solve the examples in the lecture, so you can solve the examples in the in the test. Okay.
Dr. Yani, I mean we will consider as like the ciphertext or how to encrypt or decrypt as well as the ABC method. صح؟ That the second lecture we took, you were writing
Yeah,
on the
Caesar cipher.
yeah, I think yes.
Yeah, we have. For example, I can ask you the same question. For example, I use key shift of 3 to encrypt or decrypt, just as the assignment, similar to the assignment.
Yeah, doctor. So here, how we will do it? Like we will write on a piece of paper, or how it will be done?
Actually, for me, I know that Aldar, they used a different platform for the test. But anyway, if we talk about examples with the numbers and with multiplication, I will tell you to write down and then take a photograph or take a photo of your solution and raise it or upload it. Okay.
We can upload it in that program because still we
I
don't know how to upload even.
I don't know. Me too. I didn't try it actually. But anyway, get ready for the exam. Okay.
And doctor, what is the way of the questions will come?
Actually, I didn't have the quiz in my mind right now. I will not. I I didn't write down it right now. But
Doctor, can you
for
just give
me,
us like a...
okay. For me, I'm thinking about okay. You understand? For example, Caesar cipher. If I give you any text, can you break the cipher? You can use one of the three ways to break the cipher. So I can ask you about that. Also for for the serial or the stream cipher, which we used the XOR. I can give you an example of XOR. This is the key, this is the data, and give me the input, and I give you the input and you give me the output, or vice versa. For the RSA, I can give the same example as in the lectures, or I give you different, just a little difference in the calculations for the numbers. For example, we take 3 and 7. We can use 3 and 11, for example. Can you create key, private key and public key, just like that?
And doctor, about
Doctor, this
the...
is for the today lecture, not for the quiz, right?
No, I'm talking about the quiz.
زين دكتور
Doctor,
What I was
please
talking right
وكده
now
داخلين
about
بالchapter.
how to get the quiz. Okay, let me finish the lecture first, and then we can talk in more detail. Okay, just
Doctor, because we have lab on 2:30 after 10 minutes or 9 minutes.
I know. Okay, I know. I will not take attendance. Just give me those 5 minutes. Okay. Okay. So cryptanalysis is just the trying to guess the algorithm, but the algorithm depends entirely on S-box. I told you about S-box many times in the lecture, and I told you I will speak about S-box in the future lectures in more detail. So at the beginning of this, they make that that S-box is secure. So nobody knows about how to change or substitute using the S-box at the beginning, but after that, it wasn't as secure, and using something like timing attack can have very catastrophic effect on the encryption or disencryption. So for example, in 1999, a report published showing an approach yields a harming weight using just a timing attack. Timing attack is the same as, okay, for 1 bit, what is the time of encrypting 1 bit? For 2 bits, what is the time? It will be different. So this is timing analysis, just to analyze the effect of adding or decreasing or increasing the input data and noticing the time taken to encrypt this data. So in 1999, one has discovered a way to count how many ones in the input text. This is long way compared to the original text, but it is very good step just using the timing attack. Okay, for the block cipher principal designs, you have to take care of the number of rounds, the design of the function if, and the case scheduling. These are the main concepts that you have to concentrate in any design for the symmetric key encryption. Okay, this is explaining the same thing. There are these concepts here you have to take care of, which is strict avalanche criterion and bit independence criterion. The strict avalanche criterion means, as we said, each input or each text or each bit has a probability of half to be changed. Each bit has a probability of half to be changed. For example, if I make an encryption for a specific text, each text can have the probability of changing. They have the same probability of changing, which is 0.5. This means the randomness is very accurate. If you know about probability, it means that 0.5 for each bit to be changed with a probability of 0.5 means we have pure probability. This means it is pure random. And okay, let me see something here. Just give me a few seconds. And for that one, which is bit independence criterion, this means that the output should be changed independently on the input. It doesn't mean that the change in the output, we see any change in the output doesn't mean that we have a specific change in the input. There is no relationship. This is bit independence criterion. And when you design any this, you have to take care of these also, SAC and BIC. Okay? So the first one, SAC, probability of changing is 0.5 for each bit, and bit independence criterion. The change in the output doesn't depend on the change in the input. Okay, and that's it for today, and thank you for your time. Now I stop recording.